introduction. You're going to be hearing a lot from me in this next section. So for those of you who don't know me, I'm Zalusky. I am a staff project engineer at JPI, and I've been doing LabVIEW for about 10 years. So to kick off the summit today, I'm going to talk a little bit about legacy software. And this fits into the context of our theme, which is how we future-proof our software. So the agenda today, first, we're going to go into a working definition for what legacy software is. And then the main content of the presentation is split into 3 sections. So first, we're going to talk about what design decisions we can make up front that will improve maintainability for later on. And then we're going to talk about what we can do in the maintenance phase. So basically, what are things that can go wrong in the maintenance phase of software? And I'm going to do some specific examples of how our code bases become more complex over time and kind of how we can fight that increase in complexity. And then towards the end, I want to talk about some of the other things that contribute to legacy code forming that are non-technical. So these are things related to how our teams work together and strategies we can employ to make our teams more successful. We'll have conclusions. So a little bit of background on why I chose to do this presentation today for the keynote is, as a software consultant, I interact with a lot of legacy code, and I inherit a lot of legacy code. And so this was a good opportunity to think about what it is exactly that makes code legacy code. How is it that it gets created? And kind of reflect on what are some of the things that I do or we do in our community that cause legacy code to come about. So in terms of takeaway goals today, there's a lot of content in this presentation, and I can't really do a deep dive into every section. Some of the sections I think could have been a full-length presentation on their own. But I'm hoping that this is kind of a good introduction to get people thinking about long-term implications of the changes that they make in their software. And hopefully this will be a good complement to some of the other content that comes up today. Some of the key sources of inspiration, if you're familiar with Michael Feathers, he's someone who's sort of an expert in the field of legacy code, and he wrote a great book called Working Effectively with Legacy Code. There's also a great podcast called Tech Done Right, and they have a great interview with Michael Feathers that's called Avoiding Legacy Code. And so there's some of the content, especially towards the end of this presentation, that reflects some of that interview. And then also Martin Fowler, always a great source of insight. And some of the content on refactoring and technical debt kind of comes from that. Great, so what is legacy software? There are a lot of different definitions of what legacy software is that are out there. One of the things that's kind of unique to software engineering is that this is basically never a positive quality. And when you ask people about software, legacy software, they tend to have a very strong reaction and sometimes a very dramatic reaction. So I'm going to showcase some of my favorites that I've seen. Here's a good one. That inspires terror, disappointment, disgust. This is very dramatic, obviously. It's code that might be old. According to Michael Feathers, it's any code base that's just not covered by unit tests. It's code that might use deprecated technologies. Another commonality is usually the original author of the code is no longer accessible for you to ask questions. It's code that takes a lot of effort to change. And ultimately, it's something that you'd rather scrap the entire thing and rewrite it than to try to work with it. So there's a lot of variation in how people describe it, but today, our working definition is that legacy software, ultimately, when you distill it, is software that other developers are afraid to change. And there's kind of an innate reason that we are afraid to make changes, and it's because as developers we recognize that that code is very high risk to change, and this could be due to a variety of factors. Some of them I mentioned on the previous slide, but it may be because it was not well designed or not well maintained. It may just be because it's not unit tested, it's too complex, and then insert your own complaints. There's a very long list of reasons why we don't like working with legacy code, and it makes our jobs hard. So over here I have an example, and there's an icon that I stole from one of my coworkers. Oftentimes when we start working on a project that has legacy code, we try to sort of silo it, quarantine it, and then we will surgically remove parts of the code that we need, and ultimately try to replace it all over time, so we can deprecate the whole legacy code base. So, how can we prevent our code from falling into this category? One of the things we think about preparing for the future is that we never want our code base to become somebody else's legacy code problem. And one of the ways we can achieve this is to think about how we can write our software in a way that other people are not afraid to make changes to that software. I'm going to have a little spoiler. So part of it is about the initial design, but it's not just about the initial software design. So the first section, we're going to talk about things that we can do proactively in the design phase with the aim of improving maintainability later on. And I'll preface this with, this presentation is not a deep dive in design principles or philosophy, but I'm going to just showcase a few things that we can do that will improve maintainability. So one of the first things is keeping the design simple as possible. And so we have this stream programming mantra of Yagi, you aren't going to need it, right? So we will try to design for maintainability first before other things. And sometimes this means sacrificing other good aspects of our architecture, like flexibility or scalability, for later on. So here I have kind of a classic example of Yagi. I've got my hardware abstraction layer, and I've got my nice abstract interface to my hardware. And then let's say for this specific customer, I've got a custom board, custom firmware. It's been in place for 10 years. It's very unlikely at this point that they're going to have an off-the-shelf alternative or something like that. So I may make the decision that in order to keep the software simpler for now, I'm going to skip creating this my hardware abstract class. So the idea is that we only write the software that we absolutely need now, and this will prevent some software and added complexity that may not be needed from being introduced. And another way of thinking about it is that one of the most maintainable and future-proof software is that which has the fewest number of methods that are all well-named that meet the requirements. And another way to showcase this is to think about one of the ways we measure complexity in our software, which is path length to complete an operation. And I can give an example of this. So something which would be a short path length would be, I have a method inside my class. I call that method, and then the code executes right there inside that method. That's an example of a short path length. Now let's say I need that action to happen asynchronously. So instead of having the method called and having the code, the actual work execute right there, I call my method, and then it sends a message to an asynchronous process, and then maybe inside that process, I'm going to dynamic dispatch specific work to a specific child implementation. So you can see that in that circumstance, I no longer have code executing right there where it's very easy for another developer to see. I have several levels of removal. And so that would be an increase in the path length and an increase in complexity. And obviously sometimes we need this, right? We need layers in our software. We need our software to be modular. But sometimes it's important to also think about the added complexity that those added layers add into our software and whether it's required. Sometimes it's really obvious from looking at a legacy code base why it's legacy. Sometimes you get the sense that the developer had no initial plan when they started. Typically, in this group, considering that we're all architects, it's usually other issues that come into play, aside from not having a good design strategy to begin with. And one of the things to keep in mind is that you will not always necessarily be the one maintaining your software. So we need to think, too, about the other developers who may be working with your software, and think about keeping the design simple for them as well. There are plenty of well-designed tools, and even I think internally at JDI we have some tools that are perceived as complex, and in those circumstances developers might create their own alternative tools rather than using what's already been created. So keep the design simple, that's one thing we can do. Another thing that I want to draw attention to is how we manage shared resources. And I want to talk specifically about type deaths and some things that can go wrong with type deaths if you don't manage them properly from the start of the project. So one thing that can happen is that you can create unintended coupling between classes if you don't manage your type deaths appropriately. And this may be, I've got some generic type def. It may be a cluster that contains just row, column, or something simple. And if that type def is inside a class, and I have another unrelated class that somehow gets hold of that type def, I've now created coupling between those two. When I load one class that contains a type def, it's going to load the other type def. And then another thing that can happen is it can make the boundaries between classes very painful. So this example that I'm going to show you is very similar to something that I've seen in the wild, which is that I have two classes, class A and class B. Both were developed at the same time. And these are sort of generic, so in my system, I have an XYZ data stage. So I've got a cluster that represents that data structure. And class A and class B, since they were developed independently and in parallel, each created a copy of this data structure. And the only difference between them is that the ordering of the elements between the clusters is different. So this is a big pain point when it comes for class A to actually start calling methods in class B, because each time I need to call the method, I have to rectify the difference between these two type defs. So how can we avoid that? One of the things is that unless type defs are very specific or really exclusive to the behavior in a class, they really have no business being a member of that class. If they do belong to the class, especially if they're not exposed in the public interface, make sure they're scoped as protected or private. But other things should really be put in a common and shared location, and other developers should know about it. So this prevents us from creating duplicate copies of the same type def and can save us a lot of headaches later on. And then other examples of shared resources that can cause problems are things like interlock management, path management, calibration. These are things which deal with multiple subsystems and can sometimes cause dependencies between subsystems that would otherwise be unrelated. So we need to think carefully about how we manage these, and often we need to create dedicated subsystems that will help and arbitrate between them. So this slide, this aligns with Michael Feather's definition of legacy code, which is that legacy code is simply code without tests. And one of the things that's emphasized is adding unit testing early on. So this definition goes back to what I mentioned about legacy code being legacy because other developers are afraid to make changes. So one of the things that unit tests provide is a safety net. It makes it less scary for other developers to make changes because they're aware if the changes that they made to your software have unintended side effects, or if you break functionality for existing behavior. Another thing about adding unit testing early on, so based on personal experience, I know that it can be a lot harder once a project is finished to go back and then decide that you're going to add unit testing. So this is something that we should consider early on and factor into the budget. And I know this is something that's discussed a lot in this community, but I'm very convinced at this point too that when you design your code to be testable and when you implement unit tests first, your code is better. And one of the ways that you can see that's very true is if you do the exercise of adding unit testing in later on, you can often find holes or inadequacies in your API, for example, that you would have caught if you had employed unit testing. Another thing that we can do is make sure we always have a clear roadmap to our software that's provided. It's really surprising over the years how many companies out there don't have any copies of these diagrams, or maybe they had one initially and it got lost. But this is something that makes it a lot easier for other developers to work on your software later if they don't have to go through the work of looking at the code and recreating this diagram themselves. And so this is really two things, the system level diagram, and this describes the physical system, which is always a nice overview to have. And I think this is a diagram that's more common that you will see that people have. And then also a high level software diagram. So this could be a UML, but it doesn't necessarily have to be. I know a lot of people are moving away from using UML specifically for their software diagrams. But as long as it describes the components that are in your system and the relationships between them, then that's great. And then for classes, it's great if you can create a VI tree or some live code examples that actually shows the interface to your class. This is another exercise that will also help you see if you have anything that's inconsistent in your API. So the exercise of actually making a VI tree, putting all of your public functions there, is a really good way to look at it as a complete set. Great. We should also create documentation in the code, and I think this slide might be a little bit controversial. I know people feel very strongly about exactly what should be documented, where it should be documented. But because this presentation is targeted at preventing legacy code, I think it's important that we always assume that our code is not self-documenting. For one thing, it may not be you, or it's likely not you that will be looking at the comments later. Also, if you're like me, and it's your code and you're looking at it 3 years later, it might as well have been somebody else that wrote it. But sometimes I think it's okay to describe behaviors that your code is actually doing. And I have an example here. So this is sort of an extreme case where I have a very small amount of code that is doing something very complex. And so I have a lot of documentation. And also it's great and helpful if you can add diagrams to your block diagram when things are complicated. Yes, and the other thing is, so document your code where it's most likely that it will actually be maintained and read. And for me, that is on the block diagram. So outdated documentation is often worse than no documentation at all. So we want kind of the lowest barrier to entry and lowest amount of effort for you to make changes to the documentation. And putting it right on the block diagram where you're writing the code is a good place to do it. Right, so this is kind of through the first section. What are things we can do that are proactive, keeping the design simple, thinking about how we manage type defs and other shared resources, adding unit testing, and then being thorough about our documentation. So the second part of the presentation is about what things increase software complexity over the course of its life cycle. So often we're done with the initial design and maybe even the first development phase. Our software is clean, everything's working beautifully, and then what happens? So software entropy is one thing I wanted to talk about. It's something that probably all of you are familiar with, but this is a good way of articulating what it is exactly that happens or can happen to a code base over time. And software entropy is kind of describing this as a natural process that when we make changes to our code over time, code becomes more and more complex. And it's very easy to see how this could happen. So some examples are things like it's much easier to add more functionality to an existing method than to go and create a separate method. It's easier to add another method to an existing class than to go and create an existing class. The same thing happens with the Godzilla cluster that started with 4 elements and ends up with 50. So you kind of need to actively manage this increase in complexity, and there are some ways that we can do that. But I also wanted to share this quote from Michael Feathers because I feel like it showcases this concept, which is that software becomes like biology over time. Look at a sprawling forest or jungle and get that feeling looking at a code base. So it can be really obvious when you look at a code base to know that it hasn't been maintained. You really get this organic sense that the code base is kind of growing wild. So what are some things that we can do to fight this increase in complexity? I think it was Uncle Bob that originally introduced this, but we should be proactive about refactoring. And one way to think about it is this concept of the Boy Scout rule. which is always leave the code behind in a better state than you found it. I think this is great. We should all be doing this. Another way of thinking about this, or another way that it's described, is opportunistic refactoring. What this means is that refactoring shouldn't be a separate activity that we do kind of retroactively. It's something that we should be doing continuously every day when we work on our code. And it means improving things not only for maybe the feature you're working on, but if there's a code smell or you see something else that's wrong in the nearby vicinity of what you're working on, you should take some time aside to go and make it better. Right, so if we employ this every day, it's possible that our software gets better. Refactoring in general is a good way to sort of stepwise make a change in the amount of complexity you have in your software. And it's still okay sometimes to do a more rigorous refactoring session, but we should also be doing it every day. Another related concept is this concept of technical debt. So software entropy is something more so that happens naturally. Technical debt is something that can happen either intentionally or inadvertently. I'm sure many of you are familiar with this as well, but it was a metaphor first introduced by Cunningham in the 1990s. And the debt that we're talking about when we discuss technical debt is kind of the future development time that we borrow when we make certain decisions that are aligned with short-term goals when we work on software. And you can see from this plot kind of this concept of technical debt. We have this lower curve, which is the optimal cost of change. And this is assuming that our code is well factored, it's been well maintained. There's still some increase in complexity over time because we're adding more features to the software. The code base is getting larger. But then this upper curve is what happens when we have accumulation of technical debt. This y-axis is the actual cost of change, and you can see that the actual cost of change increases significantly when we prioritize short-term thinking and we allow our code base to sort of degrade over time. And the difference between the optimal cost of change and the cost of change with technical debt is what we think of as interest. Right, so what are some ways that we can manage technical debt? One of the things that we should be doing, and we probably all do to a varying degree, but could be more rigorous about, is documenting technical debt. So this is when specific decisions are made. They may be business decisions to incur technical debt. This may be because we're striving for an early software release. We should comment or make a documentation that we made that decision and maybe even estimate the amount of time that we think it will take to repay the technical debt. And if it was inadvertent, we can document whenever that technical debt is discovered. So this is something that we should really plan for and pay back, because you can see that over time, even though a little bit of technical debt seems okay, it can become very expensive and productivity can decrease significantly if we don't manage it properly. And then another huge reason technical debt comes about, and one of the reasons why it can grow very large without being checked, is that there's a little bit of a disparity between the software engineers who are working on the code base and know what it looks like, and sometimes business managers or product managers who are making some of the business decisions about what features should be implemented and when. So it's great if we can close that knowledge gap a little bit and make this concept of code readiness part of our regular conversation with everybody. And one of the things that we can do is strive to make sure everyone involved in decision making has at least a rudimentary understanding of maybe what the software architecture looks like, and they can have a heads up when there is a huge accumulation of technical debt. All right. So now, yes.
One point there is, like, if you go back to your graph, if we focus on technical wealth instead of technical debt and start figuring out how to invest at the beginning of your curve instead of documenting debt and stuff like that, you actually get interest on the end of the curve. So that relates also to your earlier point about unit testing making budget for it. If you are doing unit testing right, yes, you're taking longer at the beginning, you should have a lot less at the end, so it shouldn't be affecting your budget. I just encourage people, I think thinking about it this way makes it, kind of gives you the allowance to be doing that. Let's encourage technical debt. Instead of talking about where can we invest so we don't have to pay back at the end.
I think that's a much more positive way of looking at it. And I think maybe originally technical debt is described in this way to help get the attention of people putting it in more monetary terms of it's going to cost you money later if you don't do it properly from the beginning.
It's the same thing if you have a down payment for a house, your interest payments for your loan are going to be a lot less. If you don't put a down payment, your interest for your loan payments are going to be higher. So it's still in monetary terms, focusing on wealth, technical wealth is better than spending time on technical debt.
Sarah, I have a question about the risk capital.
Yes.
Maybe going behind the refactoring. So how do you make the decision between maintaining interfaces and backward compatibility in your code versus refactoring, potentially breaking backward compatibility?
Right. Well, so not all refactoring will necessarily.
Please repeat the question.
Repeat the question, please.
Oh, sorry. He was asking how you balance, when you have to refactor and it impacts the interface of your modules. When do you prioritize doing that versus keeping backwards compatibility? So yeah, not all refactoring requires changes to the interface, and that's one of the things that's so tricky about designing a good public API, is that we really want this to be as restrictive as possible, because as you said, once things are released into the wild, it can be really difficult to take them back. So things which require changes to the interface require more planning, because there might be other stakeholders or other developers or other teams that are influenced. So that's something that, depending on the size of your team and depending on who else is influenced, you might have to plan more for that specific case. But hopefully a lot of the refactoring that you're doing, you're able to do inside your library or inside your class, and that it doesn't impact other developers. All right. Any other questions? So this section is basically LabVIEW story time. I wanted to give you some specific examples of how code can kind of increase in complexity during the maintenance phase, and some of the things that we can do to mitigate it. So one of the things that can happen as code bases grow and teams grow is that you may have a lot of parallel development, and you may have quite a lot of feature branches. And one thing that's important to keep in mind is that when you have a feature branch open, this is actually accruing technical debt. And the reason for this is because the longer you have a feature branch open, the more time it's going to take you to merge that change set back into the main branch. Merges can introduce bugs, and it can be difficult to maintain a lot of branches at the same time. Another thing that is a downside to having a lot of feature branches is that opportunistic refactoring that we were just talking about, this becomes more challenging, because I need to really only make changes to those few VIs that I need to implement my feature. Otherwise, the merging process is going to become even more difficult. So this is something to keep in mind. And what are some ways that we can manage this a little bit better? One thing that's recommended is if you have a very large repository, you can try to split it into sub-repositories. This might resolve some of your problems by isolating changes, but it doesn't always solve your problem, because you may be deploying feature sets that impact more than one of your repositories. So you still have some rectification of which version you need to align to have which features. Another thing we can do is avoid having a feature branch open for too long a period of time. This is something that goes a little bit against what is often best practice, but sometimes if I know it's going to take me, for example, 6 weeks to implement a feature, and I know there's a massive amount of development that's happening in my repository, it may actually be a better decision to implement it in the main branch and put a switch in there to turn the feature on and off, rather than implementing my feature in a separate branch for 6 weeks and then having to rectify merging it back into the default branch later. In practice, one of the things that happens is, I may have a release branch of the software and a default branch of the software as my main branch, and I'm probably making patches to the release branch. I also have to make patches to the default branch. And if I also have a feature branch open for 6 weeks' time, it's difficult to make patches to know where it's supposed to go, or if I need to make a patch in the default branch, if it's going to impact my feature branch that I created.
Question?
Yes.
I think that's a great point. Another workflow is you can merge, right, when you have a feature branch open a long time, you can merge from master into your feature branch, sort of proactively with the other people who might be committing to master, so you don't accrue that technical debt.
Yeah, that's very fair. It's still a point, though, that this gets messy over time, right? So if you have a lot of developers and you have a lot of branches open, you can start losing track of which branch had which set of features. And then another thing which can happen if you do get merge conflicts, we need to allocate time to manage these and also communicate very well between developers when a merge conflict happens. It's very disconcerting to have half of your feature that you implemented wiped out because somebody else merged, and it's something that you may not know right away. So you could have broken code and you may not find out for a while. Another example, when good code goes bad. So unintended coupling, especially on large projects, if you have a lot of developers, it's possible that somebody who is working in their sandbox of their module can create a new dependency, which is very bad implications for the whole architecture, but they may not realize it at the time. Here I have an example. I've got an imager system. I have 2 different flavors of imager. I have a system coordinator which controls motion in the system. And let's say someone is a developer of the polarizer subsystem, and they're tasked with creating a calibration routine. And in order to do the calibration, they need to move the stage. So they just decide, well, I'm just going to stick a dependency on the system coordinator. Obviously, they shouldn't do this, but they do it. And because they're just working in the polarizer, they don't really realize how bad it is for the system. So now I'm the sorry developer of imager A, and I load imager A into memory the first time after I merge the code. And suddenly I have imager B, and basically half the hierarchy, or the whole hierarchy. So how can we prevent this from happening in our teams? One of the things that I see happening often is that you have this beautiful software blueprint, your architecture, your UML diagram, but it really only represents the initial state of your software. This document is something that should be a live document and updated all the time. And if it's updated all the time, it makes it a lot more obvious to somebody who wants to add a new dependency what the implications of that dependency addition are to the architecture as a whole. And if the UML diagram hasn't been updated in a year, it's a lot less likely that somebody's going to go and update the diagram. So this is one way. Keeping our documentation up to date is one thing that we can do. And another thing to think about is sort of whose responsibility is it to update these diagrams? Is that one person on the team? Is that the original developer? I'm just going to go a little faster. So another thing that can happen is leaving dead code in your code base can increase code complexity. I've worked on a project recently where probably 50% of the code in the code base was all dead code. And it makes it really hard to understand what is important functionality in the software. So we should remove dead code. This is code in your disabled structure. I know people sometimes like to keep it in there because this gives you sort of a historical log of everything that's happened in the code. But this is really what your source code control is for. And it's okay to have 1 or 2 frames, but if you've got 20 frames, it's likely most of that is not relevant code. This is unreachable code, so these are maybe frames in your state machine that you never use. Any methods that are private, or typesets that are private, or parameters that go into methods that are private, these should be removed. Also, any extra VIs that are on disk that are not actually loaded into memory in your project or your class should be taken out. And then this one is tricky, and this kind of goes back to the question over there about opportunistic refactoring, which is unused, protected, or public methods and types. These are really difficult to remove once they've been put out there. So, one suggestion, first you can deprecate them, you can make them look scary so the developers don't use them. And then one strategy I employ is sort of quietly scope them as private, see if anyone complains. Another thing that happens is evolution of the God class. So this happens. This is a real example of a class, and unfortunately it scrolls a lot longer than that. Classes don't get designed this way, right? But it's very easy for them to morph into this over time. And this goes into software entropy. One of the reasons this happens is that it's a lot easier to just add another method to an existing class than to go through the work of thinking about whether or not that new feature that I'm adding aligns very tightly with the behaviors of that class. So one proactive thing that we can do is always be thinking about whether it's really appropriate to put that new method in our class or whether we need to break it into a different class. And then the retroactive solution is, large classes can be split into several smaller classes. If you're going back, reviewing your code base and you have a lot of these everything in the kitchen sink class, you should do that. And there are really obvious downsides to having these huge classes. I mean, one thing, you've made that class very, very specific. The odds that you're going to be able to reuse a class or the interface to a class that looks like this is very, very low. Another thing, it makes it really difficult for other developers who are using the interface to your class to understand what's going on. Another thing that can happen is sometimes when we optimize our code for performance, we sacrifice readability. It's great if we can make really performant code that is also readable, but oftentimes there are sacrifices that are made. And here's just one example where maybe I replaced a linear search with a lookup table and using variant attributes. And now, in order to understand the code, I need a little bit more context of what's going on because I need to understand what's inside the variant. What are my variant attributes in order to understand the code? So one of the things that we can do is add more detailed documentation when we do performance optimization. So this is sort of a review of everything that was in the second section. Refactoring, something that we should do every day as part of our daily routine. We should plan on paying back technical debt, or as Fabiola said, we should be proactive and think about how we can invest before we develop. And then keeping your documentation up to date. Also removing any dead code that's in your code base. And I think I may be short on time for section 3, which is great because I think the next presentation is on future-proofing begins with your people. And this last section was on how we can grow our teams to be more successful. So I'm just going to kind of skip through this section to get to the end. Right, so key takeaways. It's really a constant and continuous effort that's required to prevent your code from falling into the legacy code category. Getting the initial design right is important, but it's really not the whole story. And one of the most important things is just kind of caring for your code base, refactoring when it needs to, and kind of striving for incremental improvement. So that's one of the things about opportunistic refactoring is it's not fixing everything all at one time, but incrementally making things better instead of allowing your code base to, slowly deteriorate over time. All right? That's long. Thank you. Any questions? Yes.
So you were talking about opportunistic refactoring. Sometimes when I'm working, I see code that I think is bad, but I'm not sure, maybe I'm not realizing why it has to be this way. And so I worry, if I try to fix it, maybe I'll, break something that I didn't realize. How do you, deal with that?
Right, so this is tricky, and this is actually one of the things that was in the last section of the presentation is this idea of institutional memory. But one of the difficulties with legacy code bases is that there's sort of a tribal knowledge. There's a reason why somebody implemented code the way that they did. And so our tendency is to leave it alone instead of making changes. And I think the only recommendation would be, if you don't understand why it was written that way to begin with, it takes more time understanding the problem before you could be comfortable to refactor it, especially if there aren't unit tests. Because you have to be sure that the changes you make aren't going to have unintended side effects in other parts of the code. So basically, you should probably still refactor it, but be more careful. Any other questions?
You made a lot of good points. I want to throw in my 2 pet peeves. One is when you have something that needs to do a very similar function, and the lazy programmer will just make a copy of the code, and then, and it just keeps making copies. It really goes along with the entropy and the biology kind of analogy. The other pet peeve is when someone does throwaway code and then they don't throw it away. So let's just try a quick experiment to see if this works, and 10 years later you got a staff of 12 people supporting the thing,
Yes, I agree with both of those.
I had a comment. Go back to your technical debt graph. So that isn't super necessary. It strikes me that in some cases that the technical debt and your decision at the beginning to keep it simple because you aren't going to need it can be at odds with one another, right? So I'm just curious your thoughts on how to strike that balance. So that when later on when you realize, oh, I do need this feature, now all of a sudden I have all this technical debt that I didn't realize up front.
I mean, that's why we all have jobs, right? So it's a very, balancing everything that you need to is part of the hard problem. And I think when we talk about YAGNI, this is more assuming that, we're still assuming that change is going to happen, but the assumption that we're making is that we don't necessarily know what that change is going to be. So it's not saying that you shouldn't still make your software modular. Obviously, you need to do that. But there are certain decisions where the cost of making changes to your architecture later, if it's already modular, it's sort of worth the risk in not doing it now for the sake of simplicity, knowing that you may still have to implement it in the future, but you may not, right? So in the case that I showed where I end up not creating the abstract version of that class, the software is still modular, right? So if I have to go back and add it in later, I've already made some provisions for it. I just have an additional step when I have to add it where I need to then not just create a new implementation, but I have to create the abstract interface first and then also create a new implementation. So it's all a balancing act. And keeping the design simple doesn't mean not planning for the future. I don't know if that answers your question or if that's satisfactory.
Okay, the way I look at this is kind of the battle between scalability and maintainability, your question. So how much you put up front to be scalable, how much effort you put maintainable. And I think this is where a lot of times thinking about maintainability, try to ask questions to your customer where that thing is going to go in the future and put just enough in it so that you have enough scalability with a lot of maintainability. If that makes sense.
Okay, so we actually just have a 5-minute break before the next session. Thank you, Sarah.